Good morning, everyone. Welcome to class. We're going to hopefully wrap up chapter 10 here this morning. I put a couple of review problems. I think we'll have time to look at least some of the review problems from chapter 10 here today. So once we finish the notes, if we finish the chapter 10 notes today, we'll move on to a couple of review problems. And then we'll be picking up with chapter 11 after Thanksgiving break. And then a little bit of chapter 12 after we wrap up chapter 11. And then we'll be into probably a little bit of final exam review before we take the final exam 3 weeks from today. So I don't know if you looked at your schedules, but it's 8 a.m. exam, Monday of finals week for this class. I don't think a lot of you are going to want to study over Thanksgiving. You probably want to take the break. But if you start to think about studying maybe before you take off for Thanksgiving or after you get back, I would recommend taking a 1 or 2 hour study period for each chapter at some point before the final exam. Probably spending a little bit more time on whatever chapters you found to be the hardest. You could look at your exam scores, whichever ones were maybe the lowest, kind of perhaps start there, or to start as early as you need to review, and then just put the greatest focus onto those topics that you're stuck on the most. I would go to probably quizzes. Quiz yourself a lot to practice your studying. Instead of just like looking at content and necessarily reading or hearing how to solve a problem through a solution, try to force yourself to write out the solution to a problem. I think that'll help you out the most come exam time. Okay, so let's take a look at this problem here. So one of the ways we can use the ideal gas law, so we have PV is equal to nRT, and we can sub in M over molar mass times RT for mole. So this is just the mass over molar mass is equal to N. And so we can find the molar mass of a gas sample provided we know the pressure of the gas, we know the volume that the gas occupies, we know the temperature of the gas, and then we know the mass of the gas. So if we know everything except for the molar mass, we should be able to solve for the molar mass. This bulb technique here, where you can take a liquid, put it into a bulb that has a little escape point, so you can submerge the bulb in boiling water. The boiling water is going to heat up and boil the liquid inside the container. So the liquid has to have a boiling point below 100 degrees. So this technique only works with liquids that boil below the room temperature of water. But the sample ends up vaporizing. And so the compound in the liquid boils. And then you can, if you do this, sometimes we do this in lab. Does anybody know if we do this experiment in lab? I don't know if it's on our list this semester. I did it when I was a student here. And you physically watch the liquid boil off, and you're physically looking for there to be no liquid left over in that bulb. As soon as there's no liquid inside the bulb, you assume all the air particles have been pushed out. So all the gas that remains inside the container is the gaseous molecule of whatever that compound was. So you're left with those gaseous molecules in the bulb. And we push all the air out because we vaporize the sample and it's pushed the air out of the container. So we're assuming that there's really no air inside this bulb, that it's just the molecules of that vaporized sample. So once all the liquid has vaporized, and then what we do is we take the bulb out of the water bath and let it cool, dry it off from the outside so it's good and dry. You usually see a drop or two of liquid inside the container, because once you lower the temperature, the sample recondenses back into the liquid phase. But most of the liquid now is gone because most of it had vaporized and left the cell. And so we're taking the difference between the bulb after all the liquid had vaporized at 100 degrees C, and then we cooled the bulb back to room temperature. And then we're going to take the difference between the clean empty bulb mass. And if I take that difference, it looks like it's going to be 1.12 grams. So if we call this point C, that point A, we're just taking C minus A to come up with the 1.2 grams. If you notice, we put more liquid into the container. We put we put probably about 5 mils or so was usually how we do this experiment. Put a little bit of extra liquid into the bomb, so you have extra liquid to vaporize off to then fill the container with the molecules of that gaseous compound. And so then the pressure of the gas is whatever atmospheric pressure was on the day we did the experiment. So the pressure of the gas sample inside the container would just be maintained at whatever atmospheric pressure was because it's open to the container. And so the pressure here ends up just being whatever atmospheric pressure was that day, and then the volume is the volume of the bulb, we have it in milliliters here, or cubic centimeters. So obviously this would be equal to 355.3 milliliters. We're probably going to need to convert that to liters, to use our gas constant. And so then we should have everything we need to know here. And the temperature is the temperature that we were a gas. So the temperature here would be 100 degrees C. And so the boiling point of water is pretty close to 100 degrees C. If we're thinking, sig figs here at 100 versus 100.0 in terms of how precise is the boiling point of water, 100 degrees C, we'll take it maybe to 3 sig figs, but it's pretty close to 100. And so we'll say that this is 373 Kelvin, because we're going to need to convert that over to Kelvin to use the ideal gas constant. And so we should have everything we need to know here, and we'll actually plug into this equation here with the mass and molar mass in it. So I can solve for the molar mass in this equation here. So all I need to do is do a little cross multiplying. So I'll have molar mass. I'll write it over here. So my molar mass would be equal to MRT and then divide by PV. So I'm just doing the math over here, just cross multiplying molar mass over to the left side and then dividing both sides by PV. Okay, and so I have my 1.12 grams of the sample that had remained as a gas by taking the difference of the sample that had reliquefied compared to the empty bulb times the ideal gas constant. And then times 373 Kelvin. That's just 100 degrees C in Kelvin. So Kelvin's canceling. And then divide all that by our pressure. Now what do we do with the pressure here? Well, the two things we could have done, we either could have looked up the ideal gas constant in millimeters of mercury or torr, liters per mole Kelvin, or we can just convert this to ATM. Converting it to ATM is probably the easiest way to go. So let's just convert that 760 millimeters of mercury. Exactly. Let me rewrite this. So 760 millimeters precisely are in 1 ATM. So atmospheric pressure that day was a little bit higher than standard atmospheric pressure. And then the volume. So then 0.3553 liters. And so my millimeters cancels, my ATM cancels, my liter cancels, and I'm left with a unit of molar mass in grams per mole. So all my units simplify down to a unit for molar mass. So when it comes to putting this in the calculator, two options we have is obviously we'll do 1.12 times 0.08206 times 373. And then when I go to divide by, either going to do parentheses and do all the math, or I could work out the ATM math separately. So probably using parentheses is the best way to go. So I do 771 in parentheses. 771.5 divided by 760, and then times 0.3553. So I end up working out a molar mass of 95.0 units grams per mole. I say it every year, show your units. And then oftentimes I'll have, after an exam, we sit down and go over it, no units there. So units really catch a lot of mistakes. If we multiply or divide, sometimes we catch that mistake. If we get a nonsensible molar mass here, that could also clue us in. If we get something that's not like in some tens to hundreds of grams per mole, probably did some sort of math step wrong. So you can double check your math if that's the case too. Okay, so I just thought I would show this. This is how we can then get a molar mass from gas data. So, some of the chemistry problems you do with the ideal gas law are, finding quantities of gas. We did that last time. How much gas you need to fill a balloon, how much compound needed to decompose to prepare that much compound to go into the gas phase. And then this problem here, we're looking at, how can we work out the molar mass of a gas sample from some gas data. Okay, so let's push forth into the final, one of the final 2 or 3 sections of the chapter. One of them's here on the kinetic molecular theory of gases, which tries to explain why do gases behave the way they do. We've thought about this a little bit already, or some of these ideas where gases are said to be in random motion. So gas particles aren't just holding still in a sample, they're bouncing around the container. So that's why a gas maintains the shape of its container, as those particles are always in motion. We generally have gases occupy a negligible volume, meaning gases are usually just occupying a very small portion of their container, and the actual mass is really just located in the nucleus anyway. So if you remember from the idea of the nucleus contains most of the mass, so most of the atom itself is empty space anyway, so most of our actual container volume is really just nothing but empty space. Attractive forces are negligible between the compounds. We're assuming that they're not sticking together, forming any kind of like pairs. So we're assuming that if molecules hit the wall, they bounce off. If they hit each other, they just deflect off each other and bounce off and continue moving as ordinary particles. There's a constant average kinetic energy. The average kinetic energy is then related to temperature. So the kinetic energy is the idea that the particles have some mass, and that at any given moment, the sample should have the same kinetic energy. So if we look at a gas sample at moment A, moment B, moment C, the kinetic energies of all the particles should always average out to the same quantity. And what that means is, like, at some moment you might have a fast-moving particle, but then you'll have a slow-moving particle to make up for it. And if they collide together, maybe the fast particle makes the slow particle move faster, and then itself slows down. So particles, because they're always colliding with each other, are always exchanging kinetic energy. So some of the fast particles may make some of the slower particles faster, and vice versa. But on average, that kinetic energy is constant, and it's not increasing or decreasing as long as we're at constant temperature. And so kinetic energy is proportional to temperature. So if we raise the temperature, so if the temperature goes up, then the kinetic energy for the sample on average is going to go up. And so then that's going to lead the velocity to increase on average for the particle. So the average particle velocity should go up if we increase the temperature. Obviously, the mass of the particles are a constant. They're not going to change. So the thing that changes if you change the temperature is the particle velocity. So increase the temperature, particles on average move faster. Decrease the temperature on average, those particles move slower. And if you keep decreasing the temperature, the particles will move so slowly that they'll bump into each other, start sticking, and form a liquid. And so molecules can collide together according to the kinetic molecular theory of gases, but they just have to have conserved collisions, meaning energy has to be conserved through their collisions, and that they're not sticking together and forming like some sort of complex that moves through the gas sample according to this theory. And so this is just trying to describe basically an ideal gas. So this is just trying to describe how a gas behaves, so we can have a better understanding of its description. And then we can get a sense of, well, what do the sort of particle velocity distributions look like, because a sample of a gas is going to contain a tremendous number of particles. Think about having a mole of like helium. You're going to have an Avogadro's number of helium atoms, so you're going to have a wide range of velocities. So if you look at the average velocity of a gas sample, you're going to see a wide range. We'll see a graph of this on the next slide after this one. But a couple of questions here are a sample exam style question. So you have a gas that's being compressed at constant temperature. That means you're taking a gas sample and pressing a piston down upon it to increase its pressure, decrease its volume. What is happening during that compression? So as you compress the gas, are you causing the number of collisions, the frequency collisions with the container walls to increase? So if we take a gas from this volume and decrease its volume, we're going to have way more collisions with the walls of the container. So that's what's going to change. One of the reasons why the pressure goes up is because the force exerted per square area. Remember how we defined pressure as the force hitting a square area? Well, if we decrease the volume, keep the particle count the same, we're having double as many collisions with the walls. That's going to have the walls experiencing a greater force, therefore a higher pressure. And so this is what it means to have a higher pressure, is to have more collisions with the container walls. And so statement one would be that correct statement for increasing collisions because we've decreased the volume. But then have we changed the particle velocity? Now you might think, as we're compressing, maybe in the moment you compress, you kind of move things out of the way. But once they settle and you go back, we're at constant temperature, the average velocity has to be the same because we haven't changed the temperature. What it takes to change the average velocity of the particles is a change in temperature. So the temperature has to either go up or down in order to change the average velocity. If we're just compressing at constant temperature, we haven't changed the average velocity. So you may think in the very moment we're compressing, maybe we're moving things out of the way and for a moment we perturb the velocities just to have the particles move to the new location, but then they're gonna settle really quickly back to their average velocity. So the average velocity of the particles upon the compression is going to stay the same. So the only thing here, the only statement that would be true is that we're going to increase the collisions with the walls. That's going to increase the pressure, but our temperature stays constant, so we're not changing the average velocity. So let's get a glimpse at what an average velocity distribution looks like for a gas sample. And so these graphs here are trying to get a sense of what does the average particle velocity look like. Let's start with the figure B for a minute. So figure B is showing us 3 different values that are kind of relating towards the velocity distribution not being perfectly symmetrical. So if you inspect the velocity, we have almost like a long tail of velocity. Sometimes we call it a Boltzmann distribution. And you can think that what happens is you have almost like a peaking and then it averages out to long ranges. What that means is there's going to be particles that are moving very, very fast in a gas sample, and between the average and back at zero, there's not as much room to have like that long of a tail on the slower side. So we have a shorter distance here, then we have a longer distance on the faster side. So this is our faster side, this is our slower side, this is our velocity on the x-axis. So as velocity increases, we're going to have a portion of molecules at long range velocities that we still have a population of molecules with those high velocities. And so what that means is we're not going to have a perfect midpoint between like the average, the median, and the most probable. So we're going to have a few different points that we kind of label here. One of them is the most probable point. The highest point of the peak is what we call the most probable velocity. So that's the highest peak. That's the velocity that most of the particles, that the largest fraction of molecules happen to have. We then have the root mean square velocity, which is kind of complicated to explain, but it's just the velocity whose kinetic energy is equal to the average kinetic energy. So that's where the velocity point is just equal to the average kinetic energy. So if you knew what the kinetic energy average was, that's going to be the RMS velocity. So the average kinetic energy links up to this root mean square velocity. And then the average is just the simple average. So the simple, or maybe it's better called the mean, it's like the 50% point. It's the point where half of the particles have a faster velocity, half of them have a slower velocity. And so and the book uses U for velocity. I don't know why they don't use V, but I like V for velocity. The book likes U, but either U or V is velocity here. So the UMP or the VMP is the most probable velocity. The U average is the average velocity. That's the 50% point. And then the RMS, that's the root mean squared. That's the one associated with the average kinetic energy. And so we're going to see that you can actually calculate these off of the ideal gas constant. We're going to see that there is a link that the most probable velocity is going to equal the square root of 2 pi. This, I think, is on the next slide, but 2 pi RT over the molar mass. And then the root mean square is the 3 RT over the molar mass. So you can calculate the RMS velocity and the most probable velocity off of just the ideal gas constant, temperature, molar mass. We're going to need to redefine the units of R, though, just to make sure we get out an SI unit for velocity. So we're going to have to take a look at the units we want to throw all these values into, but we'll look at that on a separate slide. But the key is that some of these velocities, you can calculate them just off of their, the ideal gas law, the ideal gas constant, temperature, et cetera. And the average, I think it might be on the next slide. The average may even have a connection too. I think it's like 8 thirds or something. But there's some connection between the average point as well to RT and the molar mass. The panel A is comparing high versus low temperature. So the first panel here of the figure was showing us the difference between a low temperature gas sample and a high temperature gas sample. And so you can see that as you have a lower temperature, you just have average velocity, root mean square velocity, most probable velocity are all shifted lower. So all of our points here that we would identify around this point most probable, average about here, probably root mean square about here. We see at higher temperatures, those are all shifted over a little bit. So at a higher temperature, we have shifted the particles to, on average, having a higher set of velocities. But notice you still have a good fraction of molecules, even at high temperature, they're moving slow. You still have fast-moving particles in both distributions. You just have more fast-moving particles at the higher temperature. And so you just have a larger fraction of molecules at the higher velocities as you increase temperature, and on average, then you have a higher set of velocities. And then you also have a connection to the gas type. You have a connection to molar mass. Because if you look at, let's rewrite a couple of these equations. So the root mean square equation, this was the one that was the square root of 3 RT over molar mass, was what our root mean square velocity is equal to, and our most probable was 2 pi RT over the molar mass. That for those equations, you can think that a given sample at a given temperature, like if I'm helium or if I'm O2, if I'm a light gas versus a heavy gas, I have the same average kinetic energy at a given temperature. So they each are given the same amount of kinetic energy as a basis of whatever temperature they're at. So as long as two gases are at the same temperature, they have the same root mean square, not velocities, but they have the same average kinetic energy. So if we're looking at particles and saying, okay, we each have the same kinetic energy, but one particle mass is higher, what's that going to do to its velocity? So if O2 and helium each have the same amount of energy to distribute to their molecules, O2 is heavier, therefore it's going to have to move slower. And then the lighter particle, which has a lower mass, can therefore have a greater velocity, so it averages out to have the same average kinetic energy. So because the particles have the same average kinetic energy as each other, so two different gases, same quantity, so same amount. So we have like a mole of helium, mole of O2. The mole of O2 has the same kinetic energy to distribute to its larger molecule, so therefore it has to have a lower average velocity, lower root mean square velocity, on average a lower set of velocities than our lighter particle like helium or hydrogen. So helium, 4 grams per mole. Hydrogen's only 2 grams per mole. So as you make a particle lighter, you give it a higher set of root mean square velocities, most probable velocities, average velocities. So the distribution of velocities is increasing as you decrease the molar mass. So at lower molar masses, we're going to increase these velocities in our calculation that we can calculate for those values. I don't want to focus too much on the calculation of the velocities. It'll be on the next slide. We do have to come up with a new set of R. I think it's useful to see how we get the ideal gas constant in a different set of units than liter atmospheres per mole Kelvin. We showed them on a slide previously. I mentioned I would re-show the derivation. So let's take a look at the ideal gas constant here, just to see where this 8.314, some of you may remember the number from the previous slide, maybe you used this before, but this is the probably second most commonly used units for the ideal gas constant. But if we go back to the derivation of our gas constant, it's that we have a mole of an ideal gas, that it occupies that particular volume at STP, and again, remember STP is 0 degrees C, 1 atm. And so under those conditions, what you would do is say, instead of plugging in the pressure of that gas at 1 atm, you would say, well, what's that pressure in Pascal? Because Pascal is the SI unit of pressure. And so 1 atm in Pascal is 101.325 Pascal. That's just our simple conversion over to the SI unit of pressure. And then the SI unit that we convert here to is still 273.15 Kelvin. And the other thing we can do is the cubic meter is more often used as the SI unit of volume than the liter. So the fundamental units of the liter are defined off of a cubic meter, that 1 liter is equal to 0.001 cubic meter. So the cubic meter is more of a fundamental SI unit for volume than the liter is. And so what we do is we take our, to resolve for our gas constant in our new unit, we take the pressure in Pascal, we take the volume in liters, convert it over to cubic meters, and then we leave the mole. So this 1 mole of gas, so the mole is the same unit, and then the temperature is the same unit as it previously was, 273.15 Kelvin. And we do this math here, and then it pops out that that's 8.314. And then it'll be Pascal, instead of like liter atmospheres, it's Pascal cubic meter per mole Kelvin. And so that's the other units of R. Now, another way to express these units here would be to go back to, and again, this is just more for an educational value to see where these units come from. I doubt you'll see any tests that show or ask you to rederive these units. But if we look here, a Pascal is the SI unit of pressure, first force exerted on a square area. The SI unit of Pascal is kilogram meter to the -1, second to the -2. Well, if you multiply that by cubic meters in the unit here, then you get this to turn into kilogram meter squared per second squared. And so this unit here is just equal to the joule. So it's the same fundamental SI units as 1 joule when you work out the fundamental SI units of those two values. So again, I just wanted you to see how do we go from liter atmosphere, liter atmosphere, so volume unit, pressure unit per mole Kelvin, to Pascal cubic meter, so new pressure unit, new volume unit per mole Kelvin. So that kind of makes sense. Then all of a sudden, boom, it turns into joules. Like, where does joules come from in all of this? Well, it just comes from the combination of Pascal times cubic meters simplifies down in base SI units to just be kilograms meter squared per second squared, which is a joule. And so we find that the value 8.314 Pascal cubic meter per mole Kelvin is equal to 8.314 joules per mole Kelvin. Now, all of this kind of then goes back to if you wanted to calculate a root mean square velocity, if you wanted to use one of those equations from the previous page, we're going to want to use the SI units for R, not liter atmospheres per mole Kelvin. And so if we're asked to calculate something like the root mean square velocity for H2 in a gas sample of hydrogen gas H2 at 25 degrees C, we just have to pay attention to the units here. So our VRMS, the hydrogen mean square velocity, this was the 3RT over molar mass. And so this should be equal to the square root of 3. Now, just think velocity meters per second is an SI unit. Liter atmospheres are not SI units. So we go to the joules unit here. So we go 8.314 joules per mole Kelvin. Obviously, we want our temperature in Kelvin here. So we got to convert 25 degrees C to Kelvin as usual. I can't think of any problem in this chapter where degree C would stay degree C in a problem. Almost like I think everything in chapter 10 is going to Kelvin. And then we divide by the molar mass. But now let's think about the joule. The joule's SI units are kilograms. So it's like kilograms meter squared per second squared. So we have to go to the molar mass, but in kilograms per mole. So if we're 2.016 for hydrogen grams per mole, that would be 0.002016 kilograms per mole. And so then we need to plug this molar mass here in kilograms per mole. And then that's just because, think of the joule, it's kilogram meter squared per second squared. So the kilogram cancels, the mole cancels, the Kelvin cancels. The only thing left is meter squared per second squared. And then we're going to take the square root to go down to meters per second. So the key here, if you get a question like this, is you have to put everything into SI units. Like that's the trick, is that we just have to go back to, oh, the SI unit of mass is kilogram, not gram. And so we plug everything in here into the SI units, and we should be able to work out an SI unit for velocity. I think it's useful to see how high the velocity is too. So I get a big number, I have to take the square root. And I get 1,920 meters per second. Now, if we wanted to, we could calculate what's the average kinetic energy here for a certain gas sample. But this is that would be what the root mean square velocity connects to. So the average kinetic energy of the gas calculates that the average velocity of the particles is, or that the root mean square velocity of the particles is 1,920 meters per second. Really high velocity. So even ordinary at ordinary temperatures, gas samples have a really high velocity. Now, would you expect an O2 sample at the same temperature to have a higher or lower root mean square velocity than hydrogen? So if we're comparing the hydrogen mass or velocity we just calculated to O2, O2 is heavier. It's going to have a lower, so it has to have a lower. Now we could calculate it if we wanted to. I don't particularly want to, but if you're just plugging in a bigger number in the denominator, so you're going to get a lower velocity. Okay, so I just want to go through a little bit of the math. We don't often test the math on this. I don't know why. I don't know why we present some math and it's in the chapter and it's in problems, and then the test doesn't have a lot of the math. But for some reason, we tend not to test the math on this. More the concept that just heavier gas is slower, lighter gas is faster, and that you could connect them and calculate them if you want to, and kind of do a comparison of velocities if you knew how to plug into this equation. So I think it's good to use, good to know. You can prove the idea. You could prove O2 is slower if you just plug in 0.03200 for kilograms per mole for O2. You'll see you get a lower root mean square velocity. Let's actually see how much lower. Why not? So 3 times 8.314 times 298 divided by 0.03200, square root of that, 482 meters per second. So you can use the equation qualitatively to predict that. Higher masses, slower velocities, you can plug it in and double check and see precisely too that it's a pretty big difference. So effusion and diffusion. So the two words here, effusion is the escape of a gas from a pinhole. So gas here is being shown to escape from a pinhole. So the gas in the top half of the container is escaping into the lower half of the container through a pinhole. You can think of a hole in a tire. So you have a high pressure on one side, a low pressure on the other side. So you're going to have gas loss to the low pressure side. And so here you have your higher pressure side. Here you have your lower pressure side. And you have a pinhole. An escape of a gas through a pinhole is what we call effusion. We'll see diffusion in a minute defined, but diffusion is the escape of the flow of a gas across a medium. So it's a gas flowing through the atmospheric pressure of air. It's the flow of two gases through each other. But you can think then of the rate of escape as R1. So you can imagine there being a second particle in here. So let's call this, and let's write it more massive just to show it's bigger. So let's write a second particle in this diagram here, and let's make a bunch of these bigger particles that are each moving but slower because they're bigger. So we have particle 2 here, so we'll call that particle 2, and we'll call the red particle particle 1. And so the key is you can compare the rate of escape of particle 2 versus particle 1. Now let's also imagine that we drew a bunch of the blues in. So let's picture a diagram that has as many blue spheres as red spheres, so that we're not concerning ourselves too much with, well, there's fewer blue than there are red. So imagine there's as many blue spheres in this container as there are red spheres. And so then let's think of the rate of escape of those two gases relative to each other. Now, you might be thinking one problem is the blue particle doesn't look like it can fit, but you can imagine showing the blue particle way bigger than what it really looks like, and the same thing with the red. These particles are exquisitely small. But the rate of escape of the two particles is just going to be related to their molar masses, but inversely related to their molar masses, because you can think that particle 1 has a relationship between, either of these equations, but just the relationship to the inverse of the molar mass, the inverse of the square of the molar mass. So like R1, its rate of escape would be proportional to its velocity. And then that's going to be proportional to 1 over the square root of that particle. So how fast a particle, R1's the rate of escape. Let's make sure to define that too. So we're using R here just as to say the rate of escape, how fast does a particle escape? And so if it escapes faster, R1's higher. If it escapes slower, R1's lower. So a compound is going to have a faster rate of escape when it has a higher root mean square velocity, and then it's going to have a higher root mean square velocity when it has a lower molar mass, because we have that inverse relationship to the molar mass. And so that's how you have, like, the rate of compound 1 relates to the molar mass 1, and then compared to the rate of escape of 2 relates to the inverse of its molar mass. And so this equation here is just a complicated way of saying the lighter particle, because it moves faster, is going to hit that pinhole more often, and it's going to leave the cell faster. So the faster the velocity, think about the collision frequency. The collision frequency is higher. It's hitting the walls more often. It's just lighter, but it's going to escape through that pinhole more often. So a slower particle is going to move slower. It's not going to find that pinhole as often, and it's not going to leave the cell as fast. And so the rate of escape of particle 1, let's say, let's assume that the molar mass, like we've shown in the figure here, the molar mass of particle 1 is less than the molar mass of particle 2, so particle 1's lighter. So the escape of particle 1 is going to equal the molar mass of those two particles, the square of their differences, and then times the rate of escape of particle 2. And so the molar mass of particle 2 is higher, so the square root of molar mass 2 over molar mass 1 is greater than 1. So we're going to have a faster rate of escape for particle 1, that lighter particle. So again, we're not going to show math here. We're just thinking relative terms here, that the lighter the particle, the faster it moves, the more often it hits the pinhole. The heavier the particle, the slower it moves, the less often it hits the particles, the slower its rate. Okay, so a question on this topic is usually pretty straightforward. So which of the gases below would effuse the fastest from a tire with a small pinhole leak? Our choices are O2, CO2, N2, or they all effuse at the same rate. Well, they shouldn't all effuse at the same rate because they have different molar masses. So we're at 32 grams per mole for O2, 44 grams per mole for CO2, 28 grams per mole for N2. And so the fastest rate of escape should be the lightest particle. So it should be the N2. So if we have an air sample, now air is mostly N2, nitrogen's going to escape from the pinhole a little bit faster than the O2. You're going to still have O2 escape. It doesn't mean O2 is not escaping. It just means that the gas that's lighter is going to be slightly more concentrated in the pinhole. You can use this to separate gases. This is a technique that's sometimes used to separate two different gases that have different molar masses that you can then use. And you can do, you can imagine taking a gas sample at 78% nitrogen and then allowing a pinhole to purify nitrogen. Then you can do it a second time. So you can do the pinhole purification test a few times until you end up with a relatively pure gas. But the key is that N2 is more concentrated in the air coming out of the tire than the other two gases. And then the slowest would be CO2 because it's the heaviest gas. So we're just comparing their molar masses is all. Now, the rate of diffusion, the rate of diffusion is very similar to effusion, because diffusion is how long does it take a gas that might be here. Think of a gas in one location in the room. I like to think of the smell of something cooking or coffee being made. How long does it take that smell to reach some point in the room? Well, the particle is going to bounce around the room as it's hitting particles. So the gas molecule is not just going to go straight from its source straight to the other side of the room, because it's bouncing around all the air molecules it's running into. So the particle moves, hits an air particle, deflects this way, hits another air particle, deflects this way, and it starts deflecting all around the room. But there's multiple particles that are released. So you have all these particles being scattered through the room. So you could think, well, what really depends on how long it's going to take a particle to reach that side of the room is going to be either a property of the room, what's the pressure? So if we're at a lower atmospheric pressure, then this smell is going to get to the other side of the room faster. So I've never really done this in the mountains, but I guess if you go into the mountains and you cook, you're going to notice really quickly on the other side or upstairs that smell is going to make it there faster because you've lowered the surrounding pressure and increased the mean free path. So if we can decrease the atmospheric pressure to go into the mountains, let's say, up to higher elevation. At higher elevations, the atmospheric pressure is lower. So then you can have a faster flow because you just decreased the number of particles that the thing that's diffusing is going to encounter. So if we can decrease the surrounding pressure, that's one way we can increase the mean free path. The mean free path is how long on average does a particle travel before it encounters another particle. So obviously the lower the surrounding pressure, the longer that mean free path. You can also have a longer mean free path if you have a higher root mean square velocity or just a higher average set of velocities overall. So if you get a higher temperature, that would increase the mean free path. So if the room temperature were higher, gases are going to permeate through the room faster, assuming an equivalent atmospheric pressure. You can also look at the particle molar mass. So if you can go to a lower molar mass for your particle, it's going to give it a higher root mean square velocity, and then therefore allow it to diffuse faster. So our rate of diffusion will depend on the root mean square velocity, just like our rate of escape from a pinhole. So anything that makes the root mean square velocity faster or higher will make the rate of diffusion faster. So make the particle slower, make the particle lower in molar mass so it's faster, increase the temperature, and then also decrease the surrounding pressure in the room. Okay, so that takes us through rates of effusion and diffusion. So lighter particles move faster, they're going to effuse and diffuse faster. Now, the last topic of the chapter is real versus ideal gases. So like, when do gases behave as non-ideal gases? And we've mentioned the two situations are whenever they start to liquefy or whenever there's just too much of the gas in the container. So whenever we start to pressurize a container, go to a higher and higher pressure, then the particles of the gas are going to start to occupy a negligible portion of the container. So we have an issue with the finite volume problem. If we're calculating, let's say, the number of moles of a gas, and we're calculating off of PV over RT, we're going to get a bigger error of the number of moles at high pressures, because at high pressures, we're plugging in our container volume when we should be plugging in the free space volume. Like our assumption of the ideal gas law is we're using the container volume as if it is the free space volume, but this is not going to work out when the particles are occupying a negligible portion of the container. So this is true whenever the pressures are relatively low, because the particles aren't occupying much of the volume. But at high pressures, we're going to remove this problem. We're going to have an issue at high pressures where this won't be the case anymore at high pressure. Because you're putting more and more gas particles into the container. And so one of the ways you can fix the ideal gas law, and you'll see this on the next slide, is you can try to fix the volume. You can try to say, well, let's try to figure out how much space is being occupied by the gas sample. And we'll see a correction term, and we're going to see a correction term by a van der Waals constant B. So we'll define this equation in a minute, but we're going to see there's a B term or a B constant that's going to fix this like free space problem. So we're going to try to fix the container volume, subtract off the space that's occupied by matter as one way to fix the ideal gas law. But we can at least understand that we have a high pressure problem because our negligible volume assumption is going to no longer hold. And then we also have an attractive force problem that's going to be a low temperature problem. So we have a low temperature problem, we have a high pressure problem. So at low temperatures, particles are going to be stickier with each other. As we're getting close to a liquid's condensation point, then it's going to start to have intermolecular forces. And so if we're thinking of calculating the number of moles, PV over RT, now what moles do we get here? Is it the actual free particles? Versus having like clusters of particles stuck together. So we're assuming when we plug in a certain mass of a certain particle, we're assuming those particles are all free. Well, think about how if all the particles pair up with a partner, then we really only have half the number of moles that we thought we had in terms of the number of moles problem. So we have a mole problem. We have like a need to sort of fix the pressure that you get off of the gas particles that are stuck together. So we're going to see an A constant that tries to correct for the particles that are stuck together. So we're going to try to, recalculate the pressure that you would get back from the particles that are then like unstuck, if you will. So we're going to look at the A term that looks at the stickiness of molecules. Let's take a look at this slide here showing the comparison between that we have a bigger problem at low temperatures on both sides here. So at low temperatures, at either low pressures or high pressures, we have a problem. So we have a bigger problem at lower temperatures than we do higher temperatures. So a gas sample at a higher temperature, even at higher pressures, is getting closer to the ideal gas law prediction because we're getting rid of that like low temperature stickiness problem. So we have a low temperature and a high pressure problem here with the ideal gas law. And this is showing you which gases behave more or less ideally compared to each other. And so it's generally going to be the larger particles that behave a little bit less ideally because they're going to have a stickiness problem. We're going to see that they're generally going to have larger A constants. They're going to be stickier relative to each other. And then they're also occupying a larger volume usually. So they usually also have this like bigger volume problem. So usually being smaller for a particle makes it agree better with the ideal gas law under all conditions. And so this slide here is again just trying to show the issue of low versus high pressure. So at higher pressures, you have the particles occupying more of the volume of the container. So you have a volume issue at high pressures. And then the ideal versus ideal gas assumes all the particles are not stuck together. Well, some of the particles will form these like mini clusters, and that's going to like remove the apparent number of moles of the gas from the actual problem. So if we're trying to calculate a true pressure and some of the particles are stuck together, the real pressure is going to be lower than what we think. So we're going to have a low temperature problem here. So again, this is a low temperature issue getting close to the condensation point where we see this particular problem. And so this equation here is the way to try to fix the ideal gas law. So we're trying to fix the pressure and the volume here to be equal to nRT. So we're trying to fix the ideal gas law to take into account the volume problem that's here. So V minus NB, this is trying to calculate, well, what is the true free space volume? We're taking then the container volume in this problem here. So this is like the container volume minus N times B. So you have like a 1 liter container, how much of that volume is occupied by the matter. And so it depends on how many moles of the gas you have and then times its B constant. And so if you notice the units of B are liters per mole. So like, let's just choose a random one here to kind of like, so let's take, let's do water. So let's imagine you have a liter of water vapor. So you have a container just with water vapor in it somehow. So you have a 1 liter container, and let's say you have 1 mole of water vapor in that container. So 1 mole times the 0.30, let's run up the math here. So I'm taking 1 mole of the water times 0.0305 liters per mole says that gas is going to occupy 0.0305 liters. So if we had 1 liter of this gas, so 1 mole of water vapor inside of this 1 liter container, then the particles occupying just about 3% of the volume of the container. So not too bad. But if we continue to put more gas into the container, we're going to have a bigger issue. So the more gas we try to put into that container, then the larger the deviation we're going to have in terms of the container volume versus the free space volume. So this is a way here of trying to correct the container volume to be the free space volume. So we're just subtracting off the space that's being occupied by the matter. And then the A term is trying to correct for the intermolecular force problem. So now why would particles be stuck together? It's because they have a force of attraction. We call those intermolecular forces. We'll talk about these forces in chapter 11. This is what makes a substance behave or be a liquid under some set of conditions. And so the larger the A value, the greater the intermolecular forces. So as the A value goes up, you get a connection to stronger intermolecular forces. And then the B value here, B is going to increase as the size of the molecule increases. So now if we compare a couple values, like if you look at like helium's weird, so we're going to leave helium off this discussion. But if you look at neon to argon to krypton, notice that the B value goes up to and continues going up to xenon. So as you go from neon to argon, you're increasing the size of the noble gas. Helium has a lot of repulsion because it's so small. Helium is very weird too, that it has an exquisitely low melting point and boiling point. So it really doesn't like to liquefy. Its boiling point's like 4 Kelvin. So you get a lot of repulsion with helium that you don't get with as much with the other noble gases. But as you go up in noble gas size, generally you're going to a larger B value. If you compare like N2, look at a couple ones here worth comparing, like water to like CH4, you pick up an extra like hydrogen atom. CH4 is bigger, so CH4 has a larger B value. If you compare that to CCl4 has a really big B value because CCl4 is such a bigger molecule compared to CH4. So as the molecule is just bigger in size, the B value goes up. And then the A value is most dependent on intermolecular forces. How sticky is a molecule together? Well, helium being so repulsive, it has the smallest A constant on this chart. So as you go up in size, you're also generally going to go up in A value. But then as you go up in size and also you become a stickier molecule, you also tend to go up in value. If you look at water being 5.46, that's a lot higher than like neon is. Because you then have the possibility of like what we call hydrogen bonding, or you have a polar molecule that has a stronger attractive force. So as molecules have stronger attractive forces, the A value goes up. So we'll look in chapter 11 and try to classify, okay, now how can we look at the different types of intermolecular forces that gases have? Some gases have a weak intermolecular force. Those are mainly our nonpolar compounds have a weaker intermolecular force than the polar compounds. We'll also see things like hydrogen bonds as well. So as the strength of intermolecular forces goes up, then we're fixing the pressure in our ideal gas law. So if you notice here too, you have the plus versus the minus. You have two different ways that you have two different problems here. Fixing the volume, you decrease the volume, and then you're like adding back in the loss of intermolecular forces due to the intermolecular force of the stickiness of the molecules. Okay, now, we don't even play around with throwing calculations into this. So this problem here, we do explicitly actually say we're not going to solve math problems with this equation. We're just looking at the ideas of what do the A and the B constants mean relative to the molecule. So we can compare generally two molecules. The bigger the molecule, the bigger the B value. Generally, either the bigger the molecule of comparable intermolecular forces, the bigger the A value. Or if you're comparing two comparable sized molecules, we'll see this will depend a little bit on chapter 11 to understand this. But the stickier the molecule, the more polar it is. Two molecules have the same molecular weight. The more polar the molecule, the higher the A value, because it's going to have a stronger intermolecular force. Okay, so I think this will be a good stopping point. The few review problems I had for chapter 10, we'll just take a look at those later. But we'll wrap up today and for lecture this week with our quiz. And then we'll be back here next Monday, and we have 5 more lectures to go. So thank you guys, and have a great Thanksgiving break. Just to real quickly make sure you probably saw the announcement, but recitations do meet tomorrow. But you can just turn the assignment in if you're leaving town or if you don't want to go for tomorrow. So you can skip attending tomorrow if you wish, and just submit the activity by tomorrow night at midnight to Carmen. All right, guys, have a great day, and break.